Welcome back to the deep dive. Our mission here is pretty simple. We take these complex topics, we stack up all the source material that you send us, and we try to pull out the most important nuggets of knowledge and insight. And today, we're really cutting through all the AI hype to look at where intelligence is delivering just massive, quiet value. And that's in advanced manufacturing. But before we jump in, this deep dive is brought to you by AI Opportune.
Right. And AI Opportune is, well, it's where builders, founders, and just curious minds go to decode the real-world power of AI. If you're tired of hearing about theoretical models and you just want to know what's working right now, this is for you.
Yeah, in a world that's just full of noise, they really spotlight what actually matters, the tools, the trends, the ideas that are shaping the next generation of work and creativity and growth. They are all about practical application.
Exactly. I mean, whether you're prototyping your next startup or just rethinking your product roadmap, AI Opportune brings these really sharp insights, bold conversations, and actionable takeaways. It's all grounded in what's possible today. We highly recommend you subscribe to AI Opportune to stay ahead of the curve.
Okay, so let's unpack this. Our mission today is a really deep look at the TCL Technology Group Corporation. And this isn't just about their products. It's about how they successfully moved AI from these, theoretical experiments into reliable, real-world manufacturing infrastructure. We're specifically looking for the practical lessons inside their vertical integration model.
And this analysis is, well, it's custom tailored for a very specific audience. We're talking to startup founders, product leaders, and operators. People building AI for really complex environments, things like manufacturing, hardware, supply chains, or even climate tech. The goal here is clarity. We really need to understand how AI can genuinely work in these high-stakes production environments, where reliability, it matters so much more than just having a slick proof of concept.
Right. And you probably know TCL for their consumer products, the TVs, the home appliances. But their real strength, the thing we found most compelling in the sources, is their advanced manufacturing capacity. This primarily runs through their display subsidiary, TCL CSOT.
Which stands for China Star Optoelectronics Technology.
Exactly. And they produce LCD, OLED, and micro-LED technologies at an enormous global scale.
And their internal focus, it reflects a very deliberate, very pragmatic strategy. It's this deep shift toward what they call practical and applied AI. So they are prioritizing measured operational outcomes like better screens, lower costs, less energy, over just trying to build the largest, most abstract, generalized models. For them, AI is a tool for the factory floor. It's not just a research project.
Which brings us to the core problem, right? The one we see across the entire industrial sector. Why does AI still struggle so much in these complex physical environments? I mean, we hear endless stories of pilot projects failing or just getting stuck in perpetual demo mode.
The reasons are incredibly consistent, and they really explain why TCL's approach is so effective. Most AI projects fail because, well, first, they're built as isolated pilots that operate completely separate from the main production flow. And they often rely on generic models trained outside the specific domain. Like, think of a standard image recognition model trying to understand these super specialized defects in a chemical layer. It just can't.
And the most critical failure point, it seems to be where the AI actually sits in the architecture.
Absolutely. They sit on top of existing workflows.
Right. They just sort of observe.
Exactly. They observe the system, and then they offer a recommendation. They're not fundamentally embedded inside them, actually driving the production machinery or influencing the process controls.
That distinction on top of versus embedded inside, that sounds like a massive technical hurdle. I mean, if you're trying to embed AI into existing operational tech like SCADA or MES systems, the stuff that's been running reliably for decades, that's not a software problem, that's an infrastructure problem.
It is. It totally is. Manufacturing systems are inherently complex, they're tightly coupled, and crucially, they're noisy. Every sensor input matters, and frankly, most of them are unreliable at times. AI only works when it truly understands that context, the hard-coding physics constraints and the acceptable failure modes of the system it operates in. If you can't handle the noise and the physics, the engineers will just dismiss it instantly.
Okay, so let's look at how TCL cracked that code. Our sources identified 3 foundational pillars that allowed their AI to become reliable infrastructure. Let's start with pillar 1. Vertical integration creates better AI conditions.
TCL's whole structure is the engine here. They are vertically integrated across the entire value chain, so from early materials research in the lab through all the automated manufacturing operations and then all the way out to the finished consumer products.
And for the listener who's focused on AI, why is owning all those steps, which sounds like a very old industrial concept, why is that now a revolutionary data strategy?
Well, it provides three critical data flows that most companies can only dream of. First, direct access to high-quality, perfectly labeled production data, right from the line. No need to negotiate or harmonize external systems. Second, you get real-time feedback from factory equipment that is constantly being validated against known good outcomes. But the third one, this is the true differentiator. It's longitudinal insight. They can track a new material or a specific process change from the moment it's tested in a lab through the manufacturing line and, critically, into the finished product's actual performance and lifespan out in the customer's home.
Wow, that longitudinal insight, that's where the value just explodes. So if a display panel fails 5 years after sale because of some specific thermal issue, that data point immediately flows back to the material research team today. It's the ultimate feedback loop.
Exactly. Without it, you're just flying blind. You have no idea if the small process tweak you made last week is going to cause massive headaches 5 years from now. TCL can train their models not just on what failed, but on when and why it failed over a multi-year timeline.
Okay, but if I'm a Series A startup founder listening to this, I can't just go buy a factory. So how do I replicate that level of deep integration without millions in capital or signing these huge 5-year data agreements? Is this model only viable for industrial giants?
That's the critical, actionable lesson here. The takeaway isn't that you must own everything. It's that your AI requires deep integration. For a startup, that means you have to secure the data pathways and, crucially, the ability to influence decisions within your customer's production system. You need to become functionally vertical, even if you aren't structurally vertical. So this means integrating your technology deeply into the customer's SCADA or their manufacturing execution system, and that requires, high trust and often proprietary connectors. You are basically trying to build the functional equivalent of their internal data spine, which means you become indispensable and fast.
That shifts the technical challenge, doesn't it? It goes from building a cool model to building robust, trustworthy, mission-critical data infrastructure. That makes perfect sense. Okay, let's move to pillar 2. Domain-specific models beat generic intelligence.
This is really where the physics meets the code. In display manufacturing, specificity is absolutely everything. I mean, a 1 nanometer variation in a material layer or just a slight fluctuation in a chemical bath can have these catastrophic downstream consequences for the final picture quality or the panel's efficiency.
So general-purpose AI is basically useless here.
Effectively, yes. TCL CCT just bypasses that limitation of generalized intelligence by using internal AI systems designed specifically for display production. These models aren't just trained on images, they're trained on the physics, the chemistry, and 50 years of engineering knowledge related to making perfect screens.
So what are these domain-specific AIs actually doing that a general model just couldn't handle?
Well, they're supporting highly detailed defect analysis. So the model needs to understand if a slight discoloration is a material failure, a mechanical alignment issue, or maybe a chemical residue problem. They also handle complex process optimization, like, for example, regulating the temperature and pressure in these highly specialized vacuum deposition processes. And perhaps most critically, they're accelerating materials research. They're training models on these proprietary internal knowledge graphs that combine simulation data with historical production outcomes. And that just speeds up the development of next-gen tech like OLED and micro-LED.
That's the core insight, isn't it? That AI performs best when it understands the rules of the road, the constraints, the failure modes, the fundamental physics of the system it's in. General intelligence can talk about screens, but you need proprietary domain knowledge to build them perfectly at scale.
Precisely. You can't successfully optimize what you don't fundamentally understand. If you don't embed the physics into your model, the model will invariably recommend a physically impossible or even a destructive parameter setting.
And that focus on practicality leads us straight to pillar 3, which is my favorite because it just strips away all the hype. AI is evaluated by operational outcomes.
This is the firewall against pilot purgatory. TCL consistently judges AI by clear, hard results, not by how novel the algorithm is. Every single AI initiative is directly tied to measurable operational goals, improving yield by a percentage point, improving quality stability, reducing energy consumption in production, or supporting specific sustainability targets.
Let's talk about those results because incremental improvements, I mean, they sound small until you realize they're being applied to global scale production lines and millions of consumer products. Can you walk us through the mechanics of some of those gains?
Sure, take the home appliance examples. TCL has shown this AI-driven energy optimization in their smart air conditioners and refrigerators. And this isn't just, turning off the unit when you leave. The AI uses historical usage patterns, it learns the thermodynamic properties of the building, and it anticipates environmental conditions to optimize the compressor and cooling cycles in real time.
So it's not simply reactive, it's predictive optimization that's built on months of specific environmental data.
Exactly. And look at their smart washing machines. They use computer vision to identify fabric types, but the AI goes even deeper. Based on the fabric it senses and the water turbidity, how dirty the water is, it adapts the drum rotation speed, the water temp, the spin cycle length, even the volume of water used. It's a dynamic, closed-loop wash cycle that saves energy and water without sacrificing cleaning power.
And in the display world, they're linking display quality directly to efficiency.
Correct. Their systems apply real-time optimization to the display backlighting and the processing units. So they optimize picture quality for the content being watched, let's say a dark cinematic scene versus a bright sports broadcast. And at the same time, they're managing power efficiency throughout the whole viewing process. That is an operational outcome you can measure in watts saved and in customer satisfaction gained.
When you think about the scale of TCL's operation, a 1% energy reduction across millions of washing machines and air conditioners, plus factory optimization, that's not just a cost saving, that's like powering a small city.
Right.
That's a major operational victory built entirely on these targeted, domain-specific, incremental gains.
It is the quiet power of optimization at scale.
So let's pivot a bit. How does this AI actually function on the factory floor? We've established that reliability means human trust. How does TCL build that trust?
At TCL CSOT, the AI serves as advanced support for human engineers. It analyzes defects, not by just flagging them, but by identifying these subtle, highly complex process anomalies. The kind of thing that would take a human engineer days to find in the data logs. It just dramatically accelerates root cause analysis.
That highlights a critical distinction for trust. This is sophisticated decision support, not full automation. So the AI cuts through the noise and presents the solution set, but the human engineer remains in control of the multi-million-dollar machinery.
And that is absolutely key to reliability. When a factory is running 24/7, you cannot tolerate an AI making some unexpected catastrophic decision. Trust is built when the AI assists with precision rather than trying to override human expertise.
What's fascinating to me is that the AI doesn't stop at the factory gate. It follows the product out into the real world. Can you explain how TCL applies AI inside their consumer products to create these crucial feedback loops for future manufacturing decisions?
This is where the verticality really truly pays off. The systems embedded in the consumer products generate usage insights that are just invaluable, and they inform design and manufacturing upstream. So, for example, their smart TVs are constantly adapting picture and sound settings based on the specific content in the ambient environment of the room. And that performance data, like how the display handles heat and motion over time, which display components are stressed most often in a real-world scenario, all of that flows back to the manufacturing and materials research teams.
So the AR glasses, like their Ray Neo models that use AI for real-time translation, they're not just a product, they're actually sophisticated data collection tools. Even their experimental products, like their companion robots, they're generating interaction data that informs how they should design their next generation of processors and interface components.
Exactly. It's a complete closed-loop system, and it's powered by embedded AI at every single step. The product you buy today is essentially providing the research data for the product they're going to build 5 years from now.
This is huge. So if we're a startup founder or a product leader trying to build industrial AI today, what are the two major industry shifts that TCL's quiet success reflects? What do we need to internalize?
Okay, the first major shift is that AI is becoming core infrastructure. It's no longer a bolt-on feature or some layer you add after the systems are built. It has to be fundamentally integrated into the operating system of the physical world. So builders have to be asking, are we solving a real operational constraint, like yield or energy? Do we have persistent, high-quality access to the data we need? And maybe most importantly, can our systems survive and operate reliably in messy, real-world conditions where sensors fail and humans intervene? If you're solving a feature, you're building a pilot. If you're solving infrastructure, you're building a business.
And the second shift, how does that integration translate into a business strategy?
Integration matters more than model size. It's that simple. TCL's advantage doesn't come from owning some giant general model. It comes from tight, often proprietary, integration with physical systems, with established workflows, and with critical decision points. For startups, seeking this deep integration is what creates defensibility and long-term sticky value, even if you don't own the underlying factories yourself. You become the critical knowledge layer.
That is a phenomenal takeaway. So let's list some practical applications that listeners could adapt today, regardless of their specific manufacturing or industrial field, all built on this principle of specificity and integration.
Right. You should be focusing on things like predictive maintenance, using specific equipment sensor data to flag failures before they happen, or computer vision systems that are optimized solely for hyper-specific quality inspection on a certain material under specific thermal conditions. Energy optimization based on real-time scheduling constraints and material throughput, and AI-assisted supply chain planning that actually understands the physical laws of material transport and warehousing.
The common thread across all of those is specificity. It's built for a defined environment and a clear, measurable outcome. You're not trying to build a brain. You're trying to build a surgical instrument to optimize one specific critical chemical process by, like, 0.5%.
Precisely. That is the only path to earning trust and generating recurring value in the industrial sector.
So, to summarize the quiet lesson from TCL, AI delivers value in manufacturing when it is practical, embedded, and accountable, not when it's abstract, isolated, or judged purely by its novelty in a research paper.
Yeah, and for founders and builders, the path forward is actually pretty straightforward. Start with real operational problems that cost real money. Integrate where those critical decisions happen, go deep into the customer's technology stack, and rigorously measure what actually improves. Link it back to metrics like yield, quality, or efficiency. AI works in manufacturing when it earns trust through reliability and tangible results. And here's a final thought for you to consider, building on everything we've discussed today. If true, sustained AI value really hinges on deep proprietary domain knowledge and understanding the physics constraints of a specific system, the kind of knowledge TCL embeds in their models, then does relying solely on generalized large language models risk fundamentally misunderstanding the path to industrial success? Is deep specificity, rather than raw generalization power, the true bottleneck for real-world industrial impact?
Yes, that's a powerful note to end on. We've covered a ton of ground today, really peeling back the layers on how a massive manufacturer makes AI a reliable part of its industrial infrastructure. And remember, if you want more sharp insights and actionable takeaways on where AI is headed next, for builders, founders, and curious minds, be sure to subscribe to AI Opportune. Thanks for diving deep with us. We'll see you next time.